Hello everyone. For this worked example, we're going to determine the magnitude and location of the equivalent point load for the distributed force that's shown below. So the distributed force has got kind of a ramp up area, a flat area in the middle, and then another ramp down at the end. And so first thing we're going to need to do with the method of composite parts to solve this is break this into pieces. So in this, we've got three basic shapes. We're going to have a triangle over here. It's kind of shape 1, so it's 2 meters wide and goes up to a max of 15 kilonewtons per meter. We've got a second piece right here. It's a rectangular section in the middle. And then finally, we've got another triangular section here at the end for the last 3 meters. So for each of those pieces, I'm going to need to know the area. And I'm also going to find the centroid of this overall shape in order to find the location of the equivalent point load. So first of all, I'm going to have my three shapes, put together my table of values for the centroid location. So I've got shape 1, shape 2, shape 3. And for each of those shapes, I'm going to need to know the area. And that's going to be, the area is actually going to be in units of kilonewtons because it's meters for the width and kilonewtons per meter for the height. So kilonewtons per meter times meter gives you kilonewtons. In addition to the area of each of those three shapes, I need to know the centroid location of each piece. And that's going to be meters. I'm counting the 0 location as over here on the left. All right, so first of all, the area, let's go and find the areas of the two shapes. So the area of a triangle is 1/2 base times height. So 1/2 times 2 times 15 would give me an area of 15 kilonewtons for shape 1. For shape 2, I've got a rectangle, so just base times height, so 15 times 3, it's going to be 45 kilonewtons is the area of the rectangular center section. And then finally, the last section is going to be 15 kilonewtons per meter high, 3 meters wide. So 1/2 times 15 times 3. Area of that last triangle is going to be 22.5 kilonewtons. All right, so that's the three areas. Next up, we need to find the centroid location of each of these three pieces. So the centroid of a triangle, if we go to our tables, we'd see that it is 1/3 of the way out from the right angle side of a right triangle. So this is my kind of right angle over here. And so 1/3 of the width. So I'm going to go out 2 meters and then back 2/3 of a meter. So 2 minus 2/3. That's going to be 1.33 meters for that piece there. So somewhere around here. The centerpiece, so the center of a rectangle, is just the midpoint. So I need to go 2 meters over before I even hit the rectangle, and then I'm going to go an extra 1.5 meters over to get to the center of the rectangle. So 2 plus 1.5. That's going to give me a location of 3.5 meters for the center of the rectangle. All right, finally we have the last triangle. So I going from the right angle side of this triangle, that's my right angle there, I'd have to go 5 meters over before I even hit the triangle, and I go 1/3 of the width over beyond that. So 1/3 of 3 is just 1. So I have 5 meters to get to the rectangle, plus another 1 meter to get to the center, or the centroid of that triangle, so not rectangle. So this is going to be a total of 6. So here I've got the area and centroid location of each of my three parts, the composite parts of my force function. All right, to find FEQ, all I need to do is add the three areas. So 15 plus 45 plus 22.5. That's going to be 82.5 kilonewtons. That's the overall magnitude of my equivalent point load. And for XEQ, the location of my equivalent point load, I need to do basically area 1 times x bar 1 plus area 2 times x bar 2 plus area 3 times x bar 3. Divide that by the total area. One big fraction like this. So 15 times 1.33 plus 45 times 3.5 plus 22.5 times 6. So add those three pieces and I divide by the total area, which I already calculated, so the 82.5. So if I plug that all into a calculator, solve the math, I would get 3.79 meters. All right, so what does all this mean? Well, if I had I guess it's not a cantilever beam, if I had a beam like so, and it's assuming it's the same as the one above, the single point force that is statically equivalent to the distributed force above would have a magnitude of 82.5 kilonewtons, and it would be 3.79 meters from 0, which in this case I've defined as being the left-hand side. So this single point force is statically equivalent to my distributed force up here. All right, so that's all we're looking for. Thank you for watching and hope to see you again.